Welcome to qnawire.
All right, so this is a mix review type of problem that will combine concepts from different sections in this chapter. And as always, we should start off by drawing a free body diagram. So there's a bucket involved in this problem. So as usual, I'm just going to draw that as a square. And we should draw a free body diagram in order to see what is going on. And of course, the omnipresent force of gravity will be there. That's m times g. And then some tension force, which is being caused by the rope that's pulling on the string. Um, Note that I drew that vector longer than mg because presumably we're going to need to lift the bucket up 12 meters in this problem in order to achieve what the problem is asking for. So tension force is going to be greater than mg. We're trying to figure out the minimum amount of time it would take to lift this bucket from point A down here all the way up to point B. We'll go ahead and call that a vertical displacement of delta y. And then we want to know how long that's going to take if we're pulling it upward with this tension force at just the breaking point of the cord. So a combination of Newton's second law as well as kinematics from the beginning of the chapter. Oh, and then the last piece of information we're told is that the bucket begins at rest. That'll be important for solving the kinematics equations. So just to set us up over here, let's go ahead and apply Newton's second law in the vertical direction for this block. It's just a little fancy version of F equals ma. So we tally up our forces. Thankfully, there are only two of them in this problem. That's T minus mg is equal to may. What we're interested in for the kinematics equations, and maybe we'll just go ahead and set that up over here, is the acceleration. So I'm just writing that kinematics equation using a vertical displacement y instead of the usual x. We get a form of the equation that looks like this. So what we're going to need is that acceleration ay, solve for over here on the left. So we can go ahead and do that by dividing both sides by mass. And then at the end of the day, we'll get t over m minus g. This is not the answer, but it's an important intermediate answer. So I'll go ahead and put blocks around it. So as we saw earlier, that initial velocity is going to be equal to 0. So that helps things out with this term being equal to 0. So now we can start rearranging things and plugging things in by solving for t squared. It's going to be equal to 2 delta y over that acceleration we found. And then now would be a good time to plug that in. Where 2 is going to be equal to the square root of, let's see, t minus mg. And then at the end of the day, if we go ahead and plug it into a calculator, we will get a value of 2.58 seconds is how long it takes to lift that bucket at that breaking point. And we are all done.